DNA replication, the origami simulation. So your first step before doing anything else is going to be to do steps 1 and 2 in paper folding. First one is to fold the paper backwards along this line, which means back that way. And then the second one down here is to fold the paper this way over this line. I'm going to then complete my double-stranded DNA by writing in the letters to represent each of the parts of my molecule. So there's a key up here if you need the shapes to help you. Then I can go back in and do my bases. And the bases are a little bit harder to tell, but up here we have adenine with its 6 shape next to the sugar. So I'll put an adenine there, and if that's an adenine, that means this must be a thymine. Over here I have the pentagon shape, that's a G. G must match with C. And in fact, I'm gonna fold this over to make this a little bit easier. Label the 5' and 3' ends of the molecule. If you remember, when you're looking at a sugar that's this shape in this direction, each of these corners is taken up with a carbon, and then the very point of your sugar is an oxygen. To determine 5' and 3', you need to know which sugar is facing in each direction. So we start on the right side of the oxygen and count clockwise to identify our carbons 1, 2, 3, 4, and 5. So we know that the 5' end is always going to be the end that's sticking up the peak of our pentagon sugar. This is always going to be our 5' end, which means that on the opposite side down here, this is our 3 sugar right here in the corner, so they're 3' end. Turns out on the other side, we have our sugars are facing the other direction, the anti-parallel nature of DNA. So we would be labeling our 5' and 3' backwards of the initial side. 4, done. Then number 5 says we're going to begin replication by opening DNA, and by opening DNA, we are breaking the blank. Take a minute. What are we opening that's connecting your 2 hydrogen, to your 2 nitrogen bases? And the answer is you are breaking the hydrogen bonds. And this is accomplished by an enzyme by the name helicase. You then are going to, now that we have this open, there's our opening, we just did the role of helicase unzipping the DNA. And your next job is to play the role of another enzyme by base pairing your complementary nucleotides by drawing them in. You're going to do this, and it might take a little bit of time. You're going to start, though, as number 7 says, in the right direction, playing the role of your DNA polymerase and moving from the 5' direction of your new molecule to the 3' direction. So in order to make it a little easier, we can turn the paper so that when we draw our new molecule in here, we can draw something that will be a little bit easier. And if you can't get those shapes quite right, it's totally okay. You just want to get some type of shape in there that indicates that this is going to be an A attached to your sugar there. And then you'll have another phosphate and another sugar, and it's going to attach to another molecule here. Now our other molecule is going to start from the top, and so we can go ahead and base pair or draw in our nucleotides from this top side. Again, not as concerned about the prettiness of your molecules other than kind of indicating the difference in the shapes that we're working with. So what we represented by moving in two different directions is that the molecules, the helicase, well, if it starts unzipping here, and we'll call this a replication fork or origin. Let's say that this is where the helicase started working, moving along this way, opening up more and more DNA as it moves down here. Then we play the role of polymerase on this side, working in what we'd call the leading strand, building in a continuous direction as the helicase opens more hydrogen bonds going this way. This guy right here, though, is working in this backwards fashion. And so if this is where, at the moment, the DNA is separated to, then the DNA polymerase can come in and it can base pair starting here at this point and go down this way. But at some point in time, it's going to run into where it's already been base paired because it's moving away from the replication fork. So while building by the polymerase is happening in this direction, this helicase is continuing to open or unzip the DNA in the opposite direction. And so this strand moving away as it's being built, the polymerase moving away, is called the lagging strand.